preface this with, up until this point, we have only been asked to find the derivative of functions. So we've been always given functions that we can find the derivative and then evaluate the derivative at, let's say, x equals 7. Okay? But the reality is all graphs aren't necessarily functions. So let's say, for example, we had a graph of a circle, and we wanted to find the slope at 7 as well. Now, there would be two answers here, right? Because we have a slope up here, and we also have a slope at 7 down here, and they're obviously different. This one a negative slope, this one a positive slope. So when we are finding the derivative and differentiating something that's not a function, oftentimes it's going to, I would say oftentimes, I'm almost going to say all the time, it's going to depend on the x coordinate and the y coordinate. So we would find the slope at, let's say, 7, 3, or we would have to find the slope at 7, negative 3, and our derivative is going to include x's and y's, so that we're going to plug in the x and the y point at which we want the slope. Does that make sense? Okay, that's the general feel of what we're doing. So when we now differentiate, we're finding the derivative with respect to x still. Okay, so when we go to take the derivative of this, since it's with respect to x, when we take the derivative of x squared, we're going to do it the same way we always did. It's just 2x. And we don't have to do anything more with that, because that particular term is an x term, and this is being done with respect to x. But on the second term here, because it's y, we're going to find the derivative of that seemingly per usual, but then because this is not in terms of x, we're almost like following the chain rule, where we have to then multiply by the derivative of what's inside. And so we would put dy dx there, because that's the derivative of what's inside, equals, and what's the derivative of 16? 0. And so we're finding dy dx. So now we just need to rearrange this and get dy dx all by itself. So I would subtract the 2x over, and then I would divide by the negative 2y, and that'll simplify to x over y. So the derivative of this, not a function, I would say relation, the derivative of this relation can be determined by doing x divided by y. So we're going to take a quick time out to look at the graph of this, which is going to be, you know, an issue getting a calculator ready in and of itself. Got it. So if we want to type this into the calculator to take a look at this function, we actually first would have to solve for y. So I would add y squared over and subtract the 16 over. I just did two things at once there. And then I would have to take the square root of both sides. So y would equal plus or minus the square root of x squared minus 16. And you're not going to always have to do this follow-up step right here. I'm just going to do it to kind of give you some context for this. So if I graph this relation, and again, it's not a function. My calculator only graphs functions in isolation, but when I do both of these, the positive square root of x squared minus 16, that in and of itself is a function, and then negative the square root of x squared minus 16 also is a function in isolation, but together you're going to see that they're not a function, and they fail the they fail the vertical line test. But nonetheless, it's still a relationship. It's still a legitimate graph. Does anybody know what that's called? That would be a good description, not the title. We're usually more efficient than that. They actually came up with a word. Anybody? Aaron? No. Hyperbola, right? Yeah. It's been a while since I've seen a hyperbola. We don't do them much because they're not functions. So now if we want the derivative at any given point, we would need to, like, if I wanted the derivative or the slope of this at negative 1, 2, 3, 4, 5, at negative 5, I couldn't just plug in negative 5 to the derivative. I need to know at which negative 5, at the positive one or the negative one. So you would never have to figure this out, but if x was negative 5, I got to come up with first and foremost what those y coordinates would even be. So if x was negative 5, that would be 25 minus y squared equals 16. 25 subtract the 16 over would be 9 equals y squared. So y would equal plus or minus 3. So there's 2 points on this graph with an x-coordinate of negative 5. So we could be looking for the slope at negative 5, positive 3, or we could be looking at for the slope at negative 5, negative 3. Okay? That's this point here. That would be the negative 5, positive 3. What do you expect the slope to be there? Negative. And sure enough, if you plug in negative 5 and 3, you're going to get the slope there is negative 5/3. If you plugged in and wanted the slope at this point, which is negative 5, negative 3, when you plug in negative 5, negative 3, you'd obviously get a positive 5/3 slope, which makes sense. They're the same because you can tell that these graphs are pretty symmetrical to the x-axis. So they're the same numerical slope. The one up here is just a negative slope, and the one down here is a positive slope. Does this make sense? Okay? So this is implicit differentiation when you're taking the derivative of non-functions. Okay? Any questions? Okay. So they're going to slowly get more complicated here when we're dealing with this next one. Dealing with just this first term requires what rule? Product. So we have the first, x squared, times the derivative of the second. Now the derivative of y is 1 times dy dx. Right? Anytime we're not taking the derivative with respect to x, we need a d whatever letter dx. So first times derivative of the second, I'm not going to put that 1 in there, plus the second, which is just y, times the derivative of the first, which is just 2x. So that's your first term derivative by the product rule. Plus, and that's this big plus sign, just so we're organized. And on the second term, we also need the product rule. We have the first times the derivative of the second. What's the derivative of the second? 1, so I don't even need to write that. Plus the second times, what's the derivative of y squared? 2y dy dx. You still take the derivative of it based on your regular rules, but then it always has to be followed up with a dy dx. And then on the right-hand side, what's the derivative of negative 2? 0. Okay. So from this point forward, the implicit differentiation, the whole derivative thing, is over. Now it's all algebra skills. Now it's how do we get dy dx all by itself? Okay? Now, how many terms do we have on the left-hand side? How many terms are there total? 4. 1, 2, 3, 4. 2 of the 4 have a dy dx. I'm going to keep them on the left-hand side. The others I'm going to subtract over. So I'm going to keep the x squared dy dx. I'm going to start to get rid of some of those multiplication signs I had in there. And I'm going to keep the 2xy dy dx equals, but I'm subtracting over the y squared, so negative y squared, and I'm subtracting over this 2xy. Now, what's our game plan here? If I'm trying to solve for dy dx and I've got two of them. Good, just factor it out. So take out that dy dx, and that leaves you with x squared plus 2xy. And then just divide that binomial over. Any questions? Good. I will say this on some of them. I started with this example because it was pretty easy for me to solve for y and to give you that conceptual background of what it is that we're doing here and why we're doing it and why we need both variables. This I really can't do for you. I have no idea. It would take me a while to even come up with remotely close to what that graph looked like, because I couldn't just solve for y, given that there's multiple y squared, a y squared and a y there, and I couldn't just then type it into my calculator to see what it looks like. But know that this is a relationship, and there are points that satisfy this equation, and those points make the picture of this graph, and it's at those points that we are allowed to differentiate, and we would be able to use this equation to find the slope of this graph at any one of those given points. Dan. Moving on to the next. Now, up to this point, and you can keep doing it if you're more comfortable with it, I keep writing dy dx, dy dx, dy dx, just to kind of keep reinforcing that it's necessary because we're taking the derivative in terms of x, okay? It's a lot of writing though, to keep writing dy dx over and over and over again, so I'm going to go with like y prime moving forward, okay? Just be careful that you note that it's a prime and not an exponent of 1. Be careful of that, okay? What rule are we dealing with here? Product, okay? This will be our first, and this will be our second. So we have our first times the derivative of our second. What's the derivative of cosine? Negative sine of y. And because that was a y, we need a dy dx. But like I said, I'm going to do y prime. So that's our first times the derivative of our second. Plus our second cosine y times the derivative of our first. What's the derivative of 2 sine x? Two cosine x, good, Gina? Equals, what's the derivative of 1? 0. So we get negative 2 sine x sine y times y prime over here. No, because this was the second term just carried down as it was. I didn't take the derivative of it. This was the second times the derivative of the first. So the second I just carried down, and the derivative of the first, that first term was already in terms of x. So I don't need anything because I am taking the derivative with respect to x. Does that make sense? Okay, good question. Plus 2 cosine x cosine y. And my goal here is to get y prime all by itself. So I'm going to subtract this guy over. and then I'm going to divide both sides by this. My negative 2's are going to cancel nicely. And I'm going to have cosine x cosine y over sine x sine y. How could we potentially clean this up, Alex? Very good. Your cosine x over sine x would give you a cotangent x, and your cosine y over sine y would give you a cotangent y. I want you to try that last example on your own. Confidence. What are these names on the top? Thought you were trying to name my child. I'm looking. Those are some nice names. What? What did you say? Owen, that's not appropriate. Okay. How do we feel about this? I would like you all to play teacher. I can fix the blur, I think. Uh-huh. You don't need to raise your hand, though, for those points. Who wants to pick one? Okay, Dylan, go ahead. Maggie. So you don't know what he did wrong? Lauren? No, you don't. I'm not even sure that would make it easier for you. There may be some cases where rearranging the original could simplify it, but I'm not sure that this is one. That would make it any easier. Owen? Aaron? Oh, classic order of operations mistake. So he keeps the first line is all great. His derivative is perfect. Now the rearranging for y prime, I told you this is the algebra part. This is unfortunately where we're going to struggle because it's messier algebra than you've ever had to kind of clean up before. So he did subtraction prior to doing multiplication, classic PEMDAS mistake. So what should have happened is we really need to get our y prime on the same side. So if I add this is technically minus 1y prime. If I add that over, it would just be y prime minus the cosecant squared minus the cosecant square of y times y prime equals 1. And so now I have two terms, both of which have a y prime. I factor out my y prime. I'm left with 1 minus cosecant squared of y equals 1. Divide both sides by the binomial. And that's your dy dx. I wouldn't want to. Because if you did change that cotangent into cosine over sine, should it work out? Yes. It's going to be incredibly messy because if you do cosine over sine, and by the way, they're both of y, which is what makes it tricky. You're going to do your bottom times your derivative of the top, which is going to require a dy dx, minus your top times your derivative of the bottom. The derivative of the bottom is also, because this is a y, going to require a dy dx. And so then, and then your right-hand side is going to have a dy dx, so you're going to have 3 of these floating around. Not good. If we have a derivative that we're supposed to have memorized for cotangent, for that reason. So we don't have to split it up and use a quotient rule every time. Aaron. Yes. So this is a Pythagorean identity. Okay, remember, your Pythagorean identities come from sine squared plus cosine squared equals 1. The one that involves cosecant is by dividing everything by sine squared, right? So everything divided by sine squared would produce a 1 plus cotangent squared equals 1 divided by sine squared would be cosecant squared. And then 1 minus a cosecant squared. And then I'll subtract the cotangent squared over. Will equal a negative cotangent squared. So y equals 1 over negative cotangent of y squared. And that's the reciprocal of cotangent. So what's that? Oops, my squared should be on the inside. Sorry. What's the reciprocal of cotangent? Tangent. So it's negative the tangent of y squared. Sierra asked me this morning if we were done with trig, and I thought I didn't really remember that this was trig. I told her no. She had a little awakening, huh? So, all good there? Now for whose is this that I took? Whose was the second one? Oh, Bryce. Can you pass that back to Dylan, please? Bryce's first step. That's a multiplication, I think. Yeah, I gotcha. And then you didn't really do much else. You just kind of stopped. So you didn't make a mistake. You just didn't go anywhere with it. All right. Good. That was a good exercise. Try the next one on your own. Oh, Aaron, you get a point, right? About you taking your time in silence to try a problem. When you're ready, the answer's up there so you can check it. Raise your hand if you got that on your own. Good. Any questions on it? Say that one more time. No, so we're just, it is the chain rule. 3y squared times the derivative of what's inside, which is y prime or dy dx. I obviously stopped writing dy dx just because they were ugly. All right, the next one, write small. On the left-hand side, what's going on here? This is, and I'm actually going to rewrite this as xy to the 1/2 power. So on the left-hand side, when I jump into the derivative, what rule is going to trump all other rules to start? Chain, good. Well, power chain, yeah. So I have 1/2, and then I have xy to the negative 1/2, and then I need to multiply that by the derivative of what was inside. Now, what was inside was xy. How do I have to take the derivative of xy? Product. Good, Maggie. xy is a product rule. So we have, and so I'm going to do a big set of brackets around this to make sure that whatever I have here, this initial coefficient has to get distributed. So I have my first, which is x, times the derivative of my second, which is y prime, plus my second, which is y, times the derivative of my first, which is just 1. So that didn't end up being so bad. That's the left-hand side. Equals. What's the derivative of x? What's the derivative of negative 2y? Very good. Negative 2 times y prime. So I do have y prime in a couple places here. Before I get to that, I'm going to clean this up. This is 1 over 2 root xy. Agreed? Times, and I'm going to keep everything else the same, xy prime plus y equals 1 minus 2y prime. What do I have to do in order to get those y primes together? I have to distribute, okay? It's not something, I don't want to have to distribute something that's ugly, but I really can't avoid it. So that first distribution is going to lead to xy prime over the ugly radical plus y over the ugly radical maybe I like that. Maybe that looks prettier. And now I can move all my y prime terms to the left and my non-y prime terms to the right. So I'm adding this guy over. And I'm subtracting this guy over. Comes next, Owen? Factor out the y prime. And then divide that over. This is why I said very small. I'm going back up. So y prime is going to equal this 1 minus y over 2 root xy, all divided by x over 2 root xy plus 2. So our derivatives, at least our y prime is all by itself now, but we do still have some cleanup to go because we have a complex fraction. Now, most of you have preferred in the past to get a common denominator within the numerator, to add those two terms, to get a common denominator within the denominator, to add those two terms, and then you keep change flip. Not the most efficient all the time. Okay? We talked about another method earlier in the year, but none of you really gravitated towards it. But if you look at all of the denominators within your fraction, so the denominators of the fractions within your fraction, if you just multiply by the least common denominator over itself, and in this case it's clearly a 2 root xy. In other words, multiply the overall numerator by 2 root xy and the denominator by 2 root xy. That's going to clean things up so much more quickly. We have to distribute that into the numerator. Times 1 is no big deal. And times the fraction is what is really the whole reason and purpose for this. Works out nicely because that cancels the denominator, yes? So it's just minus y. And that's your overall numerator. And we also have to distribute this in the denominator. When we distribute it to the first term, again, this will cancel with the first term's denominator, leaving just x. And this times our second term, 2, just makes it a plus 4 root xy. And there's your answer. All right. last one we'll get started on. We'll just get started. What derivative rule is going to trump this on the left? Chain, power chain. So bring your 2 out in front. Leave this inside completely untouched. Technically, that exponent of 2 just got dropped to an exponent of 1 times the derivative of what's inside. Now, the derivative of what's inside is probably going to be a binomial, so I'm going to use a big set of brackets here for organizational purposes. What's the derivative of the sine pi x? Cosine pi x times pi. There's a chain rule within just that derivative. Good? Well, just because I like to keep it in order for people so they know I do the derivative of the sine pi x times the derivative of what's inside. I will eventually put that in front. Okay, and some of you are already at the point where you would naturally just squeeze it out in front just so it's already more organized. I just get nervous doing that because if people are following the work, you really don't process that appearing until after the fact. Okay, then on our second piece of this binomial, what's the derivative of cosine? Okay, so negative sine of pi y times the derivative of what's inside of that. Now, what's the derivative of pi y? Very good, Sam. Pi y prime. You tell everybody today that by the end of the day they'll be saying pi y prime. Pi y prime. Sounds like a password. If you ever get locked out, that's our password. Pi y prime. Right? Well done over there. And then from here it's going to be cleanup, but I wanted to get through that first step. And getting y prime all by itself here is not terrible. Keep in mind though, this whole thing has to be distributed to this whole thing. Actually, no it doesn't. Let's avoid it altogether. There's no y prime in here, so why worry about it? If we divide both sides by that immediately, what happens? Cancels out. That's a huge time saver. So then it's pi cosine of pi x minus pi sine of pi y times y prime. And now getting y prime all by itself is not much of a big deal. Subtract this over and then divide that coefficient. Emily. We're taking the derivative of cosine pi y. So the derivative of cosine is negative sine. So we have to start with negative sine of pi y times the derivative of what's inside. Okay? Your homework's down there at the bottom. Have a great week.